In this video, we're going to work on sketching waveforms without a table of values, based on the information that we know about the amplitude and period of a trig function. In this first example, we outline the steps to graph the trig function y is equal to sine of 2x. First, we will determine the amplitude and period of the waveform. From looking at our original function, y is equal to sine of 2x, we see that a is equal to 1. It's the implicit coefficient in front of our sine 2x function, and b is equal to 2. Therefore, our amplitude is 1, and our period is 2 pi over b, or 2 pi over 2, which reduces to pi. In step 2, we lightly sketch a rectangle. The left edge is the y-axis. The length of the rectangle is equivalent to the period, and the height along the y-axis is the amplitude above and the amplitude below the x-axis. Making the instructions from step 2 a reality, we want to lightly sketch our rectangle. On our y-axis, we show the amplitude above and below the x-axis. So we have positive 1 and negative 1. Now the length of my rectangle is equal to the length of the period, and that is along the x-axis. Should also mark where my y-axis is. And now we need to sketch the rectangle. Now we can see that the height of our rectangle is equivalent to 2 times the amplitude, and the width is the period. Step 3 says to subdivide that same rectangle into 4 equal parts, and we're going to use those subdivisions to mark the zeros, maximums, and minimums of the waveform. To subdivide this rectangle, I typically divide the entire thing in half and then divide each half into quarters. And what we can do is label these values along the x-axis, because we know that the entire width of the rectangle is pi, halfway is going to be pi over 2, and then we have pi over 4 and 3 pi over 4 as our other two subdivision points for the rectangle. Step 4 says to lightly sketch the sine curve. Recall that our curve begins at 0. So before we try to sketch the curve, we should mark our maximum, minimum, and 0 values. So our zeros occur at 0, at pi, and halfway at pi over 2. And remember that the sine curve first opens up, so we have our maximum halfway between our first two zeros, and then our minimum occurs at 3 pi over 4. And now we're ready to sketch the curve. Try to connect these points by nice smooth lines. And because this is a cyclical function and repeats periodically, we can use lines to indicate that the function continues and goes on forever. So this is a quick sketch of our function y is equal to sine of 2x. We could do the same thing with different amplitudes and different periods as well. Here we have a practice question where we're going to identify the amplitude and period of the function y is equal to 3 sine of 4x. For this function, we know that a is equal to 3 and b is equal to 4. Therefore, amplitude is equal to 3, and our period is equal to 2 pi divided by b, which is 4, or pi over 2. Now we can sketch a rectangle by identifying our amplitude. So we have positive 3, equal distance away from the x-axis. We have negative 3, our entire period is pi over 2. So we have one full cycle of this sine curve within that distance from 0 to pi over 2. Now we can subdivide that into 4 different sections. So first I'm going to draw my rectangle. Notice a ruler is handy here. My Surface doesn't allow me to use a ruler with it, but I trust that when you're making your sketches, you will take the time to use a straight edge and make better subdivisions than I can show here. So since we have pi over 2 for one period, this will be pi over 4, and we can further divide it into the 4 sections where we have pi over 8, and then 3 pi over 8. Because we have 4 equal sections, our sine curve begins at 0, 0, so we have a 0, 0, 0, a second 0 at pi over 4, so halfway, and another one at the end point. And because our a value is positive, our function will increase, and we'll have a maximum of pi over 8 and a minimum at 3 pi over 8. And connecting these points with a nice smooth curve, we get an initial sketch for the function y is equal to 3 sine of 4x. We actually have enough space here to show a second period of the function. So what we could do if we wanted to show 2 full periods is continue graphing up to pi. Because if one period occurs in pi over 2, then a second period will occur by pi. So you can re-subdivide these rectangles, and you can just watch here and see what the second period looks like. It's pretty normal for students to have a hard time dealing with fractions in terms of pi and how to denote them on our graph. So just to show how I landed at each of these intervals, I'm going to show the subdivisions. We know in this example that one period occurs at pi over 2. So within pi over 2, we have one full cycle of our function. And if we want to find a quarter of pi over 2, so each of those quarters are going to be in pi divided by 2 divided by 4. And what we do with the 4 is we're going to invert and multiply. So you're multiplying by 1 over 4, and the result is each quarter has a length of pi over 8. So if our x values then begin at 0, be 0 pi over 8, so 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. If we continue into a second period, we get 8 pi over 8. Let's just do one more, 6 pi over 8. And the markings I showed on my graph are the simplified values. So if we reduce these to the lowest terms, it's 0 pi over 8, and then pi over 4. 3 pi over 8 can't be reduced anymore, but 4 pi over 8 reduces to pi over 2. 5 pi over 8. And 6 pi over 8 reduces to 3 pi over 4. So hopefully that's helpful in coming up with the intervals for your x-axis. Next we'll be looking at shifting waveforms along the horizontal axis, as well as moving waveforms up and down by considering a midline shift. It takes a while to get used to graphing trig functions, so make sure you get familiar with your basic sine and cosine functions, as well as translating them, given the methods shown in these notes. Also, ask questions from your professor if you have any. It's really good to verify that you understand what you've learned in these videos.